Hello, everyone. Can you hear me from the very back? Okay, I will keep this voice. Thank you for um, in this evening in your private time, and also thanks for the organizer of this event. Also thanks for eBay Connect at Germany for your invitation, and for okay. Maybe first I need to mention one thing. This talk may take about 40 minutes. If there's not that much question, if there's many questions, then it may take longer. So my suggestion is that if some people who already feel hungry, you can already take some food. Otherwise, it's not good. I'm not sure if this is okay for the organization. Okay. Okay, so if you feel hungry, feel free to pick up some food, which is prepared over there. And now I will get started. Today, I'm going to talk about work I did in my previous job. I just joined eBay 4 months ago, and the current work that I'm working on is not ready for present in public talk yet. But I do have something to present from my previous work. And it's about detecting activity patterns. For example, jogging, cycling, sitting, sleeping, walking, etc. And detect these activity patterns from accelerometer data. For accelerometer data, you can imagine it's a data connected from accelerometer like a watch or like a smartphone. Using one type of deep learning neural network, it's called the convolutional neural network. We will detail this later. And very short self-introduction. I joined eBay a few months ago, and I founded my own company. It's just a part-time work. I want to do applied deep learning. So DL means deep learning, and applied is applied deep learning. For mainly two services. One is offer training. Second is conducting projects. But we can skip this part. And this is the contact information and my collaborators. Okay, let's directly go to our outline. So we are going to first talk about what is the problem, why it is important, how we solved it, and what's the future directions. For what's the problem, we will introduce how does the accelerometer device look like, how does the data look like, and how does the data set that we have been working on, the data set is from NISPello, which I will also introduce later. This is the device look like. It's like a watch. And we're connecting accelerometer data from 3 axes, X, Y, Z, respectively. And this is how does one segment of the data look like. We can see that it contains 4 columns. The first column is the date, time information. And from the second to the last column, they are the data from X, Y, Z axis, respectively. And we also say that all these numbers, they are between the range of -1 and 1. Maybe you expect that the data is in the range of -9.7 between and to 9.7. The 9.7 is the Earth's gravity. But this data set is normalized. We normalized by the power of by the Earth's gravity. So it's in the range. If the activity is not that big, so it's in the range of -1 and 1. But when there's a huge activity, then the data can still be bigger than 1 or smaller than -1. This is one piece of visualization of the data. As you can see, I left my office and walking to the train station, sitting on the train station, and walking to my bicycle, and then cycling to my living place. This is the zoom in of those parts. We can say, by our eye, we can see that there's a big difference between walking, sitting on the train, and cycling. And by the way, you are free to interrupt me if you have any question during this talk. So by looking at here, by human being, so we have confidence that these different type of activities could be detected automatically using computer. And then introduction about the data set we worked on. We have about 805 accelerometer recordings connected from NIS parallel. And NIS means Longitude Internet Study for Social Science. This parallel is maintained by my previous employer. And this could be interesting for a Dutch audience, but for German audience, I don't think so. So let's skip this one. But this parallel do connected a lot of interesting data, and they are public available for research purpose only. So if a researcher in Germany, you can still make use of the data. You simply go to this link and then ask for access, and you can use it for free for research purpose. You can see it contains rich data like gender, age, income, living conditions, almost any aspects about social science that you can imagine. And they connect this data set on a monthly basis. It has been collected for about 1 decade. And next goes to the why this is important. So the goal of the study was to first detect activity patterns from these recordings. They are pre-recorded, and during the recording, there were low labels. So they are unlabeled data. But we still need to figure out what the possible activities for those participants from the NIS parallel. After we detected the activity patterns, then we tried to find out the relationship between activity patterns and other aspects of the social science information, like what's the relationship between jogging pattern and the health status. And for me, my major responsibility was to detect the activity pattern. And one of my colleagues worked on finding out the relationship using my result and the other social science data in that database. Compared with the questionnaire, this kind of measurement is more objective. Because questionnaire, people may answer the questions subjectively, but measurement is objective. And then compared with video surveillance, the accelerometer is more long-invasive in privacy. So people are willing to cooperate with this data connection. If it's video surveillance, then it's very difficult to do that. And then move on to how we solve this problem. I will introduce it from two aspects. One is approaches in literature. Second is our own approach. I will show two slides. This is one slide. Second is this slide. This slide using conventional machine learning methods. The second one using deep learning method. There are some common things within these two slides, and there are some differences. So let's start from the common things. For these two slides, each chart has several columns. The first column and the last column, they are the same for the two slides. So the first column is about data connection using different devices connecting the accelerometer data. The last column is what we want. We want to classify it into different activities like running, cycling, etc. The difference between these two slides, basically between the conventional machine learning methods and the deep learning methods, is that it lies in the middle part of this chart. We can see for conventional machine learning methods, we have two columns in between. The second column is feature engineering. So we need to manually design feature from the raw data. The feature we can think of could be based on statistical methods like variance, mean, max, standard deviation, etc. Could also be based on frequency, like the frequency, like the DC component, like amplitude, etc. After we manually design the feature based on the raw data, we can use this manually designed feature as input to the classifier in the third column. And then this is classifiers, they are conventional machine learning methods. We can think of k-mean neighbors, support vector machine, etc. Then the difference between the conventional and the deep learning is that the deep learning methods merged the second column with the third column. It means that there is no manual feature engineering anymore. All the features used by the classifier is automatically learned within the neural network. And this is the main reason why nowadays deep learning outperformed the traditional machine learning methods, because the features, they are optimized features. They are learned automatically from the data. We do not need the manual design, feature engineering anymore. I hope I conveyed the message clearly. Okay, let's move on. This is a summary of the deep learning approaches to solve this activity pattern recognition problem. From this chart, we can see that the CNN, the convolutional neural network, is the dominant method among all these methods. After reading the literature, we figured that these CNNs, most of them, they used a very old version of CNN. So CNN itself, so convolutional neural network itself, is developed very fast in the computer vision community. There is a competition. It's called it's hidden by this symbol. This challenge started in 2011, and then last year, so 2017, is the last year of this competition, because it's already suppressed the human level performance. It's not necessary to host this competition anymore. And we can see that almost every year, there is a new new type of convolutional neural network was published. And there are at least two things we can see from this chart. The first thing is that with the year going on, the number of layers grows dramatically. Second thing we can see is that with the year going on, the top 5 error of this challenge goes down also dramatically. So now we come up with a question. So can we make use of the advanced convolutional neural network in our case to process our accelerometer data? There is some challenge involved because these advanced convolutional neural network, they mainly used in the computer vision domain. They were used to process images. And images, they are two-dimensional data. They have image width and image height. In our case, even though we have 3 channels of data, X, Y, and Z, but for each channel, it's one-dimensional data. So the question is, can we apply this advanced convolutional neural network, which is used mainly for two-dimensional data, into our case, which is one-dimensional data? And then that's the reason why we started to apply this. And we pick up this one. It shows that it's the run-up in 2014. It's not the a winner, but it's a run-up. The reason is that it's the structure of this neural network is very simple and it's very easy to implement. And next, we are moving to our approach. We will then split this into 2 aspects again. One is the overview, one is the details. Because I feel that it's challenging to give a public talk to a diverse audience to make sure that a general audience were able to follow. And at the same time, to make those advanced audience feel interesting. So that's why I divided it into 2 parts. For the overview, it's mainly for general audience, you can easily follow. And for advanced audience, we can dive into the details. But of course, the general audience, you're also welcome to dive into detail together. Overview. So as I said, when we received the data from NIST panel, they were collected a few years ago and they were unlabeled. How to tackle this problem? It's a typical classification problem, but we were missing the label. We do not know what's going on in those unlabeled data. To solve this problem, we started the data connection. We used the same devices and started connecting data within our company. We started from very 6 easy activities like cycling, driving, jogging, sitting on the train, sleeping, walking. And we adapted a model, as I said, from the GoogLeNet, 19. 19 means the number of layers. And then we trained 3 models for different segment lengths. They are about 5, 10, and 20 seconds segment length. Using the GPU of Dutch supercomputer. The company I worked for, in my former company is a research institute, so we had a free access to the Dutch supercomputer. And then tested the models on the 905 NIST panel recordings using the Google Cloud services. Yeah. The data set that we connected by ourselves. We carefully labeled the data. So for the so we connected the data for training, and then applied the trained model to the NIST payload data, to this 805 NIST payload data. Two different, yes. Yeah, we have to solve the problem on the data set we connected a few years ago by using the data that we connected by ourselves. Any other question? Okay, let's move on. Okay, as shown on this slide, it's very easy actually to convert convolutional neural network model from two-dimensional into two-dimensional. This is a list for all these changes. We can see it's easy to understand. For the input shape, for images, we have length of channels, image height, and image width. In our case, we also have length of channels. We have 3 channels, but we only have segment length. We do not have image width. And then for the convolutional layer and the pony layer, okay, these 2 layers, they are basic elements to build up a convolutional neural network, which we will introduce further in later slides. We simply use the one-dimensional version of these 2 layers. And for the kernel size, you may not understand what does kernel mean, but we will also introduce later. Kernel size, for image process, we use 2-dimensional kernel, 3 by 3. In our case, we are processing 1-dimensional data, so our kernel size is only 3. And for model complexity, because our data is not as complex as those challenging, so we reduce the complexity of the model by reduce the number of layers and reduce the number of filters in each layer. And the last thing that we choose the sigma mode as the nonlinear function of the last layer of the model instead of softmax. I will also introduce why we did this later. This is just an overview, so do not worry if you do not understand. And secondly, we train the model. After we build the model, then we train the model using Dutch supercomputer. This is just a job file to submit a job. It's also very simple. This would be interesting for Dutch audience because they may have access to supercomputer, but it would not be interesting for our audience here. But I think in Germany, you also have national supercomputer, which you can use if you are from research institutes. Then in the following slides, we will show the performance of the trained model on using different segment lengths for training. This is the performance using about 5 seconds, about 10 seconds, and about 20 seconds. We can see that if we use shorter segments, then the performance, so the last column, becomes more fluctuates. If we use longer segments, then the performance becomes more stable. And the segment length itself is a hyperparameter we need to play with. We need to try different segment lengths and pick up the best one. And then using the trained model, we tested using Google services. So I received a question previously, in which situation we can use these Google services. What I can imagine is that in a situation when you want to process huge amount of data, not that often, only for example, only for one time, then you can launch huge amount of powerful Google virtual machines and then process it and then shut it down. Then by doing so, you do not need to buy hardware by yourself. That's the situation I can imagine when the Google services is useful. We only use the 2 services. One is computing power, basically it's a virtual machine. And second is storage, because data is large, we need a Google storage. This chart shows the price of a Google virtual machine. Maybe it's too small for you to say. what I can simply show is that for this virtual machine with one GPU with 4 GB of memory, the monthly cost is about 30 euro. And the Google charges on hourly basis, not on monthly basis. So for each hour, it's about 0.04 US dollar. Then I think this is very cheap. I think it's even cheaper than the power supply if you use your own machine. And this is a trick when you use, yes? Yes, only for, no. During the testing phase, we do not need a GPU anymore. So we simply use CPU to finish the testing. And there's another small trick. So before we launch huge amount of virtual machines, we tested on one machine to see what's the best configuration. It means that what's the best CPU and what's the best memory I need to use, because the CPU and the memory, they are most expensive thing when we launch virtual machine. So we launch the one, and we figure out the best configuration such that we can make use 100% of the CPU and almost 100% of the memory. And this is also a good thing about cloud, the virtual machine on the cloud, because you can tune the configuration of the virtual machine such that you use the virtual machines more economically, so you do not waste resources. And this slide shows maybe it's also too small. This is I borrowed from my colleague. He is doing post analysis based on the results that I provided to him. It's about the first row is about snipping. The second and the third row is about one is jogging, one is walking, and then each column is representing day of a week. We can see that in the middle there are 3 days. People sleep less, but do sports more, or walking or jogging more. And then Monday and Friday, people can sleep more and do sports less. This could be caused that in the Netherlands, a lot of people, they simply took 1 day off, either on Monday or either on Friday. Then they can have a longer weekend. Then it means that on weekend, people can sleep more and do less sports, or walk less, or jogging less. Let's move on to details. And you are free to ask questions and to interrupt me. And all of you, not only the advanced audience, all of you are welcome to dive into it with me. Okay, this is the outline of the details. So the convolutional neural network is one type of deep learning, as I mentioned. And the deep learning itself is nothing but a neural network. So we will start introducing what is neural and what is neural network in a mathematical perspective. And then introduce convolutional neural network, and then the VGGNet, which is a specific type of convolutional neural network. And then we will talk about how we adapt this neural network for our application. And then the last part is data pre-processing. I heard that when we do data science, about 80% of the time is spending on preparing the data, cleaning the data. 20% is about building the model, training the model. So a lot of, also in our slides, a lot of slides is also about data pre-processing. So let's continue. This is one neuron. Can you imagine what can this neuron do? It has output Y, except the input X. There is a key times this X, and then it will plus a B for that. this is what this neuron do. It's a linear regression for one-dimensional data. This, I think this chart is maybe you can see from high school mathematical textbook. This is one linear neuron do. And what can we do if we have multiple neurons or a neural network? In the next slide, we have 2 neurons. And what can this neuron do? Now we can see that we have 2 layers. One is input layer, one is output layer. And if you compare this mathematical formula, y equals x times a dot product my w and plus my b, if you compare with this mathematical formula, it looks the same, right? It's a linear relationship between my x and my y, using the parameters k and b for one-dimensional cases, or using the parameter w and b for multi-dimensional cases. And we can give an example of this. We can see that maybe the input could be, the output could be classify a human being into a male or female. So Y1 means the probability that this human being is a male. Y2 is the probability that this human being is a female. Based on 3 types of information, we can think of 3 types of information to classify a human being into male and female. We can think of the height of the human being, the weight of the human being, and the length of the hair of the human being. Right? I think the length of the hair of the human being is most informative to classify a human being into male or female. And then this is the dimension of the input. We can make it more general. We can generalize it into this case. So in this case, x is 1 by m dimension. So basically, we are going to connect information about a human being. We are going to connect m types of information about a human being. And then y is 1 by n. In our case, we are classifying human being into male or female. So this 1 is 1 by n. So it's 1 by 2 in our specific example. And then this w is m by n. And then this b is 1 by n. This is a more general case of to analyze this neural network, which contains 2 neurons. Any questions so far? It's quite easy to understand, I think. Okay, let's continue. To make this is a linear model, but the complexity of the linear model is not good enough. Then to increase the complexity, we could add the nonlinear function to this linear part. You can compare the mathematical formula on the right top. Compare with previous slide. Previous slide is y equals x dot product w plus b. Now I have a nonlinear function f surrounding this linear part. And the nonlinear function is sometimes it's also called activation function. This is I provided an example of it on this slide. It's called sigmoid. And then to further increase the complexity, we could have a chain of layers to build multiple layers of neural network. And in this case, it shows not only the input and the output layer anymore. In between, there's a layer, we call it hidden layer. And look at this mathematical formula here. It's simply a nested way of matrix multiplication and the nonlinear function. So I would make this statement. So the deep learning neural network is nothing but the matrix multiplication and plus some nonlinear process. Any questions so far? Okay, I think it's still easy to follow. Okay. So my question. So this slide, we can see that we can add up layers one by one to build a deep learning neural network. Is this that easy to build a deep learning neural network? Then the next slide shows that no, it's not that easy due to this vanishing gradient problem. This is the fundamental problem of deep learning. Why? So what is the vanishing gradient problem? So first, what is the gradient? And the gradient is the gradient of a loss function with respect to the parameters of my model. In our case, we have all these parameters in red color, W and B. These parameters, they are model parameters I want to train using training data. When the model is trained, these parameters, this W and B, the value will converge. They were randomly initialized, and after training iteration by iteration, these parameters, they will converge to a stable matrix or vectors. So what is loss function? I already mentioned the gradient of my loss with respect to my model parameters, but what is loss function? Loss function is the loss when the model is not able to classify your data correctly. That's the loss. So you have the output of your model, you classify your data from the you received from the left side, classify it into certain classes on the right side, but you have the true value for this data. Then you compare the output of your model with the true value that you have, then you can see the difference. When the model cannot classify correctly, then there's some loss in this network. Then we need to reduce the loss. By reducing the loss, we need to calculate the gradient of the loss with respect to the model parameters, which is shown here in red color. And then using this gradient information, we can train our network. Next. Any questions so far? Okay, still easy to follow. Okay, next, I will quickly introduce the first generation of the convolutional neural network. This example shows that the convolution, this neural network can be used to classify images and the traffic signs into digital numbers. In this case, classify this image of 60 into a digital number 60. So we need to we analyze this model by breaking it into two parts. There's a big part in red color. In red color, this big part acts as a feature extractor. It extracts a feature from the raw image, from these raw pixel values, into some feature. And then this feature will be applied to this classifier. And then this classifier will eventually classify it into different digital numbers. So now I already break down this entire model into a feature extraction part and a classification part. Now we break this feature extraction part further into two parts. This part and this part. These two parts, they look different with each other, but in principle, they are the same. Why? Because both of them, they contain two layers. Both of them, they contain two layers. The first layer of each block is convolutional layer. The second layer of the block is called a pooling layer. These are the two basic operators to build up a convolutional neural network, which we will introduce later. Okay, I think this we made it clear. Okay, now as I said, the basic elements to build up convolutional neural network is a convolution layer and a pruning layer. Now we will introduce what does these two layers do. For the convolution layer, how can you understand it? So this area which is moving is a sliding window which is moving over the entire image. So at the back, this green matrix represents the image. It contains pixel values. And this sliding window itself, it also has values. It has, in red color, it has values. These values are model parameters that we are interested in. They are not predefined, but they are randomly initialized and then trained adaptively during the training phase. So all these red colors in this sliding window, they are changing over time during the training phase until reach the optimized model parameter. So now we know that there are two metrics. One is this sliding window. It's a matrix containing these values in red color. There's a second matrix, which is the image, which is the part of the image covered by this sliding window. These two metrics will do element-wise multiplication and then sum it up, then provide it to this output image. So I will repeat again. So this sliding window will do element-wise multiplication with the part of image covered by this sliding window, and then sum it up. And then the summed value will be provided as the output, will be provided as a pixel value of my output image. Any questions so far? No? Okay. This sliding window is moving. You can see it's sliding. So it slides from the left top till the right bottom. First move horizontally and then move vertically. And of course, you can now in this demo it shows that this sliding window slides pixel by pixel. But you can slide 2 pixels by 2 pixels or 3 pixels by 3 pixels. That's hyperparameter you could play with. And also the size of the sliding window. Now it shows a 3 by 3 sliding window. You can use 5 by 5. You can use 7 by 7. You can play with the size of the sliding window. It's a hyperparameter you could play with. Left side shows the pruning. What does pruning do? As shown by this figure, there are mainly two types of pruning. One is maximum pruning, one is average pruning. As the name suggests, the maximum pruning, so the values within this block. Now for do pruning, I also need a sliding window. In this case, it's 2 by 2 sliding window. And within this sliding window, these values are the pixel values of the image covered by this sliding window. In this case, I have these 4 numbers covered by this sliding window. And then if I do maximum pruning, as the name suggests, I will pick up the maximum value among these 4. If I do average pruning, I will pick up the average value among these 4. Then I have my, and for maximum pruning, normally we move this sliding window without overlap. You can also do, this is also kind of a hyperparameter. You can move, you can define the pixels when you move, but normally we do movement, we move this sliding window without overlap. Then it means that the size of my output image will become half. if I choose 2 by 2 sliding window. Can you imagine? Because if I remove result overlap. Okay. Any questions so far? So I have just finished introducing the 2 basic operators to build up convolutional neural network. Later on, we will spend some time introducing a VGG model that we are interested in. We adapted the model from this VGG model into our application. Compared with the first generation of convolutional neural network, what we can see. So these boxes in red color, they are pruning layer, it's maximum pruning. And then these boxes, they are convolutional layers. The difference between VGG and the first generation of convolutional neural network is that for the first generation convolutional neural network, every convolutional layer is followed by a pruning layer, as shown here. Every convolution layer is followed by a pruning layer. But in this VGG model, it could be that several convolutional layers followed by one pruning layer. Can you see the difference? Okay. This is the code, part of the code, which shows how we implement our model. As I said, we convert the 2-dimensional convolutional process into 1 dimension. We changed the kernel size from 2-dimensional, 3 by 3, into 3. And also the pruning, we use 1-dimensional pruning. But this is not important. The important thing is that we use very small kernel size, basically very small sliding window in the entire image. In our case, it's 1-dimensional data, so we use very small. It's only a sliding window containing of length 3 for the entire model, you can see. For the entire model. What's the reason behind this? So the complexity of the deep learning neural network could go in 2 directions. One direction is wider-wise. Basically, the wider it is, the more complex it is in the wider-wise. Which means that with larger sliding window, using larger sliding window, then the complexity of the model become more complex in wider wise. It could also, the complexity could also go in depth wise by using more layers instead of a wider sliding window. And can gain more benefit by increasing the complexity of the model in the depth-wise, and that's why deep learning is so powerful. So we want to have more layers instead of a wider sliding window. And for short, it's this. We prefer thin and deep. So this in this. Yes. So this thin and deep concept in this convolutional neural network domain is first introduced by this publication, and we can see this publication. This publication, this VGG network, is a network introduced in 2014. And later on, in 2015 and 2016, there are also at the same year, in 2014, there's a GoogleNet, All these networks, they follow the same concept, which is thin and deep. And also different models, they introduce the different good concept, like the GoogLeNet, they introduced the idea of batch normalization, which is not a part of our talk, of course. But what I want to say is that there's a reason behind these advanced models. They introduced some good concept. The thin and deep concept is a good concept introduced by this VGG model. Any questions so far? Okay. This is ResNet. ResNet is a nonlinear function. Previously, we introduced the one example of a nonlinear function, which is sigma mode. ResNet is another nonlinear function. Of course, this softmax is also another nonlinear function. But in our case, we do not use softmax, but we use the sigma mode. I will introduce the reason later. Here shows the mathematical formula of three most frequently used nonlinear function, and also the plot of this nonlinear function, together with the first order gradient of this nonlinear function. So I think for the ResNet and sigma mode, it's very easy to understand, and also the chart is very easy to understand. The softmax is more complex to understand. How to understand it? We simply regard this part. So the C, the capital C, is number of classes. In our previous example, it's we have two classes, male and female. In our real application, we have three classes, three types of activities. So this is the meaning of capital C. It's a number of classes. This part is nothing but a normalization. By doing so, this part represents the probability that my ith data point is classified as so it's the probability that my data point is classified into my ith class. Okay, that's it. And the vanishing gradient problem, we already introduced before. Why? So there are several reasons needs to this gradient vanishing problem, which is a fundamental problem of deep learning. One reason could be the improper nonlinear function that we used. For example, if we use the sigma mode function for all the layers, what the problem it will be? You can see this is the first order of sigma mode function, and the maximum value is 0.25, so it's 1/4. This is a small number. Every time when I calculate the gradient passing nearby layer, I need to multiply with this gradient by following the chain of gradient calculation. You can see this is very. If I multiply with this smaller number for many times, the times is equals with the number of layers. Then with more layers, this for these beginning layers, I will have very small gradient information because of this continuous multiplication with this smaller number. And then when there's very small gradient information, then some parameters associated with these layers are very difficult to be trained, because we need to train our model based on the gradient information of my loss with respect to these model parameters. But when the gradient information is very small, then we are not able to train these parameters and more. So this is why this name is called the vanishing gradient problem. Next slide, I want to show some loss function. Well, I already explained. The loss function is the loss when my model misclassified my data. What I show here is there are two tables. This table is the output of my model. This table is the true table. It's the true class of my data. And I showed two examples of the loss function. One is called the categorical cross entropy. One is called the binary cross entropy. These two loss functions, they are very confusing for deep learning beginners. So what's the difference between these two? So for the categorical cross entropy, it only maximizes these green values. For the binary cross entropy, it will do one extra thing. The one extra thing is that it will also try to minimize these yellow values. So the binary cross entropy not only maximizes these green values, but also minimize these yellow values. Any questions so far? Okay, let's continue. I think this chart is very self-explanatory. Let's move on. Now this is now we go to the data pre-processing step. We did several data pre-processing tricks. This is one of them, which is called shallow merging. We want to, with the purpose of doing so, is want to get rid of rotation influence. So when I have my accelerometer at my wrist, when I only do rotation movement, then after apply this function, I would only see a stable line, because rotation movement does not contribute to this can be a kind of normalization to remove the rotation influence. Can you imagine? Because when there's no transitional movement, only rotation, then after apply this one, apply this function, I still get a very stable line. Can you imagine? Okay. The next step is called the streaming. What does streaming do? So when the data, so we need to do streaming in a situation that my data set is big and does not fit into my memory. So I need to store my data on this disk, on a disk, and then read my data into memory in a streaming way, and then train my model batch by batch. This is the reason why we do streaming. Clear? Okay. Next, random shuffling. Why we need to do this? So there are two spaces, input spaces. They are identical with each other. Each dot in this space is one data point, one segment in our case. If I do not randomly shuffle it, so which is shown on this left chart, then every batch, because I train my model batch by batch, every batch comes from a local area in my input space. And then we can say that the difference between batches, they are different, they are quite different. For example, the first batch I get these local points, second batch I get these local points. Then it makes really difficult for my model to converge, because the difference between different batches, they are so big. What you will observe if you do not randomly shuffle, what you will observe is that the performance of your model will fluctuate a lot of vibration. By applying random shuffling of my data points, it means that for every batch, I randomly pick up some segments from my entire data set. By doing so, each batch is kind of evenly distributed in my entire database, in my entire input space. And then by doing so, the performance of my model will converge gradually. Clear? Okay. Augmentation. What does this mean? So this is a very simple augmentation we did. What we did, we randomly pick up a point in this segment, and then we swapped the order of these two segments. Then after swapping, the segments look like this. But we still call it walking. It looks quite different from each other, but we still call it walking. By doing so, the reason is that we can have more training data, more labeled training data at a very low cost, almost without the cost. Because it's really time-consuming to get labeled data, to label the accelerometer data. I think, okay, yeah. No, after I took a segment of sequence, the length of segment is a high performance you need to play with. You can use 5 seconds, 10 seconds, or any number of seconds that you want. You can try. Then randomly pick up a separating point. In this case, it's randomly pick up this point. And then I get 2 parts, and then swap the order of these 2 parts leads to this new segment. There are much more tricks you can use to augment your data set. This is only one of the most simple way to augment the data set. Now we have finished the detailed part of our work. We are going to move on to the future directions. Any questions so far? Okay. So first, we want to get more labeled data. But it's not easy. We could look into public available dataset to see whether they have free public available labeled data. We could also do cloud sourcing by taking advantage of the cloud to allocate the data. For example, ask our colleagues to do that for us. Second is in terms of model. Second direction is in terms of model. We pick up the VGG because it's very easy to implement. We could also try other advanced convolutional neural networks. And then these deep learning neural networks, they have too many ways to be trained. We call it a heavy-weighted neural network. But what we prefer is a kind of neural network which have the similar performance, but with much less weight. We call it light-weighted deep models. Then certainly, we need to fine-tune the hyperparameters, like the number of layers, size of kernels, different activation functions, and different loss functions, etc. And then in terms of learning strategy, currently the model, they are pre-trained using the labeled data that we connected, and then apply the model to the dataset. When train the model to the dataset, we did not train the model anymore. What we could do is that we could make use of active learning, which is, you can imagine a scenario when you have a watch accelerometer on your wrist, and your watch continuously recognizes what you are doing, but at some moment when your watch is not able to classify what you are doing, then your watch could actively ask you, hey, what are you doing? Then you will say, oh, I'm watching on TV or doing something else. Then your your watch can actively learn when they feel uncertain about what you're doing. And then for the incremental learning, it means that as soon as the watch has new labeled data, they can continuously embedding this knowledge contained in this new labeled data into the current model. So the model can learn incrementally. In terms of application, we can think of at least one of them, which is called the assistant. So what does this mean? Computing systems are aware of the activities of the user such that they can proactively assist the user. This is the general idea about the assistant. A specific example is that when you have this watch at hand and when you are jogging, then your watch knows you are jogging, then your watch will turn on your hot water automatically such that you will have hot water at the right moment when you arrive your home. So you do not need to cool your hot water 24 hours. You can save energy for that. This is only one example of assistant. So this is an overview of all the future directions. I also would like to hear your feedback, how this can be further improved. It will be very valuable for this application. And then, thank you very much. This is the take-home message. We wanted to try whether the two-dimensional, whether the convolutional neural networks, which were mainly used for processing two-dimensional data, like images, can be converted into process one-dimensional data. And the outcome from our experiment is that yes, we can, and it's easy. And the second message is that NIST parallel data contain rich information and is publicly available for research purpose. And then thirdly, if we want to train deep neural network, we prefer a GPU computing machine. And Dutch supercomputer, which you can use it if you work in Dutch research institute or Dutch hospitals. Google Cloud Services, in a situation that you want to have a huge amount of computing power, but for very short-term usage, you can think of Google Cloud Services. We also introduced at least 3 types of activation functions, 2 types of loss functions, and we spent a lot of time talking about data preprocessing, for example, streaming, random shuffling, and augmentation. Thank you very much.
Thanks for this very clear talk.
Thank you.
I had a question, and you mentioned in your future directions about the hyperparameters that you could still optimize.
Yeah.
So I noticed also on your code slide that all your layers had the same parameter settings.
Yeah.
So I would like to ask if this is common, that all the layers have the same hyperparameters, and how would you go about finding the best parameters here, because it's such a data-heavy job. So what are the techniques? Can you just make use of the classic machine learning ones, or are there some special techniques to find the best hyperparameters in deep learning?
Yeah, okay, thank you very much for your question. This is a very good question. I will try to answer your question in using the following points. So the first point I want to make is that maybe you observed that for the entire model, I used the color size of 3, and I use activation. Actually, this one I initialized before. I initialized as ReLo. So I use ReLo nonlinear function for the entire model except the last except the last layer. The reason is that ReLo has a very good property, and it's the default nonlinear function if you do not specify any nonlinear function. And then this maybe could answer you why I use the same parameters for some of the hyperparameters for the entire model. And then secondly, you also asked whether there's some trick to tune the hyperparameter. What we can think of is called a random grade. So we randomly choose different hyperparameters and then find a region which have the high probability leads to good performance. And within that region, we do random search again to further find out the exact hyperparameter. But that involves a lot of computation. So fine-tune to find out the hyperparameter is not an easy task to do. And did I answer your question? Okay, thank you.
Thanks for the talk. I had a couple of questions. I start with the question which I think is most important. What was the data and how big was it that you used for training? I thought that was those sets that you were talking about. I don't remember how many, 800 something, 2.4 petabytes.
Let's see, here.
Or terabytes, sorry, it was terabytes, I think.
Oh, where is it? Here, we connected 3 types, and for different activities, we connected different lengths of the data.
Yes, sorry. I mean, what is between those like 5, 10, and 20 seconds segments? You need raw data, right? Where did you get the raw data, and how much was that?
You mean this?
Yes.
This part. We read the data in a streaming way from the data that we connected, and the data we connected for different activity, they have a different lengths. For those activity, we can easily connect and easily enable. They have a longer duration, like snipping. We can easily connecting days or few weeks of snipping data. For jogging or for cycling, they are more difficult to connect. Then we have only few days of those data from different people.
So was this data part of this LISS panel recordings? No, I understood before that this was only used after training.
Yes.
And you had a different data set for training.
Yes.
So how much data did you have for training?
As I said, for different, we connected 6 types. And for those types, which we can easily connect a huge amount of data, like snipping. I can easily connecting snipping data for a few hours, for a few days, for a few weeks. Then we have more data. For other activities, like cycling, like jogging, it's more difficult to connect. Then we have a few days of data connected from our colleagues, different colleagues.
From colleagues, right?
Yeah, from colleagues.
Okay. And you don't have a number like how much data that was?
In terms of days, for this cycling and jogging, this kind of more difficult data to be collected. For the snippings, we have more than 10 days of data. Yeah.
That's true. But for me, as a practitioner, it's always super important to understand real sizes of the input data sets and to understand the effect of different sizes on your training approach. Because for me, I have to always understand what kind of input data I need to have a valid case. That's what I do every day, so that's why this would be very, very interesting for me to understand really, and if you would have compared different sizes of input data sets for your training, and also, of course, then to see the effect on the accuracy.
Yeah.
That would be something that I would call a test, for example.
Okay. So in our case, this study is a very initial study. We want to have a quick result, simply to prove the concept. So we choose the most simplest model which we can implement it quickly, and we pick up these 6 type of activities we can relatively easy to connect. And then to improve it, we need to label more data. For these 6, in our daily life, we have hundreds of thousands of activities, but we only collected these 6 activities which we can easily connect it.
Okay, thanks.
Yeah, thank you. You're welcome to ask a question and also provide feedback for improvement. Yeah. 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 Mm-hmm.
Yes, then you can basically combine these 6 activities with the trained data and apply all of them to the raw data from any other source you have. This, for example, LISS.
Yeah.
And out of LISS data, you then can predict those 6 activities. Like not predict, but choose this activity is one of these 6, right?
So we train the model using the 6 activities we connected, and we apply the trained model to this niche parallel, this 805 recordings.
Mm-hmm.
And this to apply it is simply for testing, because
Yes.
this data are unlabeled, so we cannot get knowledge from those unlabeled data. We simply apply it.
Okay. Once again, here, I mean, when you train something about cycling,
Yeah.
you're training only cycling without any other data in this data set. I mean, you always have this label that you are training only cycle part now, right? Or maybe
no. So each time we rate the same amount of segments from these 6 activities.
how? Okay, now I get it.
Yeah.
Thank you so much.
So every batch contain these 6 activities, and the amount of segments for each activity is the same, in order to have a balanced training data set.
Yeah, now it's clear.
Yeah,
Thank you.
Yeah, okay, thank you. Yeah.
So how did you actually come up with your data augmentation technique? Because did you compare your results before and after, or did you actually use it only to increase the sample size? Because
Sorry?
I'm thinking like, how did you come up with your augmentation technique? Did you actually
Okay.
like compare them?
So the augmentation technique was not invented by me. I borrowed the idea from the image recognition challenge. So for the image recognition, if in the image there's a cat, then if we rotate this image or we flip this image vertically or horizontally, the cat is still there. They still call that image of cat. So that kind of tricks we borrowed from the image recognition community.
No, I mean that, but that's a little different, right? Because that makes sense because you want to teach your algorithm to understand the cat from different angles.
Yeah.
But I'm just wondering, like, how, like, if it makes a lot of intuitive sense also when you talk about augmentation in this sense for walking. Like, did you actually compare it? Like, did you compare the results without augmentation as well?
To be honest, no. We directly implement this because we think augmentation is a good thing to have. So we directly implement this augmentation. We can maybe we can further argue why this would be useful. You can see I have a segment here. The only change is sweeping the order, but it already leads to huge difference in terms of the shape of the signal. We only swept the order, you can see, but the difference is already huge. but we still need to call it walking. We do not do any other process, we only sweep the order. So it basically means that I swept my walking pattern of later few seconds in front of my previous few seconds of walking. This makes sense, right? Because it's both segments, they are walking. And we only swept the order. We should call them still walking because we only swept the order. Yeah.
Thank you.
Again, what's the strategy? I cannot quite follow. Thank you.
So the alternative, for example, augmentation strategy would have been to have a sliding window and generate 5 seconds from 0, 5 seconds from after the first 1/60th of a second, then 5 seconds, second 60th of a second, etc. That would be a different augmentation technique, and you could have compared the two. I think that's what.
This is a good idea to have different training set, and this is exactly what we used. Because as I said, for example, for the snipping, I have an entire line of snipping. Then I should use a sliding window to randomly pick up segments.
So you also did sliding window and
yes.
also did this?
For after we get segment, using that sliding window, then within this segment we do not apply sliding window anymore, because this segment, they are gathered using a sliding window. We use a sliding window through the entire line of snipping, for example, and then get this segment. So this is already a sliding window involved. But after we get this segment, we do not apply sliding window further because.
Sure. Thanks.
Yeah. Okay, thank you.
I just wanted to ask about your pre-processing again.
Pre-processing.
Because this is. I just wanted to see if you had some drift or other artifacts or something that you had to correct the data for, or if you just left it. So you said you did some normalization, but I just wanted to ask if you had to correct the data for something like drift or artifacts.
Okay. Yes, indeed. When we do data processing, this is the typical data processing problem. There are always some noise involved. The drift you mentioned is a low frequency noise, so it's moving very slowly. It's a drift. And there are also some high frequency noise, like this spikes. And in our case, we did not pay that much attention into data filtering of those noise, because we do not have a good knowledge about how does the noise look like. If we want to remove it, our human beings should have a good knowledge. How does those noise look like? What's the frequency range of those noise? But at the time when we do this research, we did not know this. So we simply accept very raw data as input and apply the deep learning to do this kind of data cleaning for us. Thank you.